Hello everyone, it's September, December, December the 26th. Alright, so before we start, first thing first, contest. So I was saying I might not be able to do the contest yesterday, but at the end I still did and didn't do very well. You can see I only solved two problems, so it was worse than the previous week. And if you take a look at the time, right, the first problem was pretty fast, and the second one I spent the entire time. So basically, the second problem, actually, I can go back to the problem. I go back to the problem. So the second one is an interesting problem, right? It's you're given a position of a robot and a grid, and then giving you a list of orders that it can go, and asking the question asks if starting at each position of the order going down, how many steps can we move before the robot gets out of the grid? Now, I spent a lot of time on this because I was trying to figure out a smart way to do this. It feels like I can reuse the results. Like if I'm starting from the first position, going all the way down, and then I'm starting from the second position, maybe I can use the information I already collected before. And it might be possible. Yeah, it might be possible. And I tried. I tried pretty hard trying to get this. But at now I spent an hour and a half on this almost, and I couldn't. There was no way I can figure out a good scheme that's generalizable for all situations. I mean, the best I can do is compute the maximum displacement horizontally and vertically, starting at each position, so we can tell whether we can go through the entire thing. Right, easy. If I can go through the entire thing, then that can make it fast. But if I can't, then I just have to go step by step. I just couldn't figure out a way. So eventually, with I think maybe 5 minutes left, I was like, ah, screw this. I'll just do it the stupid way, which is just starting at the same position. I would just go through all the positions, all the orders, and see if it's out or in. And it passed. Like the brute force way passed. So maybe it is brute force. Who knows? I mean, after the contest is over, I was pissed and I'm very angry. And I decided to do this. And surprisingly, this is a good problem, the interval between identical elements, and I actually solved it. So it was a little bit consolation, right? A little bit consolation that, well, even if I only did two, if I had, just skip this one and then move on to this one, then maybe I will be able to solve this, and then coming back to this, we'll be able to solve it as well. But I didn't. I got stuck on this problem for the entire time and didn't have time for this, which actually I can solve. What should I say? I mean, this is a good problem. It's a good one. I like it because I think I had a pretty smart way to solve it. I also wrote a post. I'm not sure if anybody has read it, but I mean, two take home. Well, it's gotten stuck. I mean, two take home message from this contest experience. First, um, if something seems like you can try with brute force, just try it. I mean, worst case scenario, we got a penalty, right? But it's fine. I mean, at my current stage, I don't care about penalty. What I care about is solving all problems within a given time. So I should just go with the brute force and see if it works. And the second of all is if I got stuck, I should move on. I mean, this is the old trick. I know this since elementary school, middle school, high school. Whenever in an exam you got stuck in a problem, just give it up. Don't spend too much time. You move on. You try to finish the others, and then you come back for it. I mean, in this case, if I had done this one, I switched this problem earlier, I would have solved this, and then we'll go back to the previous one. I probably got discouraged and then go with brute force. So I might be able to solve all three. So who knows, right? But yeah, this one I think I did it pretty well. And I see, I'm not sure And it's not going to be most vote. I think I wrote it yesterday. Nah, I don't think I can even see it. Where is mine? It's meaningless. I mean, is it possible this one has a better solution? Yeah, it is possible. Oh, a lot of people posted. Where is mine? Right here. I got 20 views. I got 20 views. But no upvote. Alright. Anyway, so that's that. So today, the goal is, of course, we're going to solve the first problem. Yeah, this guy from the same college as I do. So the first goal is to solve today's problem. Detonate the maximum bombs. Yeah, so the first one is to solve today's problem, which is this one. And if we can solve it in a short period of time, I'm going to try to tackle this one. Recover original array. So I'm going to put it there. But this is under context, so you know what? No, I shouldn't do it here. I should do it here. Go to the last page, and then just open it up. Maybe we have time to solve it. We learn. I mean, it's a contest, so I shall bring in a different mindset, right? If it's a contest, then the goal is to solve the problem, however means possible. That is that is the game that we're playing. That's the game we're playing. All right. Anyway, so let's start from the first one. It's a new problem. Wow, very rare. Okay, k closest points to origin. Given an array of points, where points I is this, represents a point on the xy plane, and integer k, return the k closest points to the origin. The distance between 2 points on the xy plane is Euclidean distance, that's true, as the order answer is guaranteed to be unique except for the order that it is in. So basically we need to sort. Hold on, isn't this just sorting? How many points? 10 to the 4th. It's not too bad. You can sort based on Euclidean distance and take the first 2, the first k. Let's see if it works. I mean, there's always a likelihood that this is not going to work, but I mean, Python has a key. I can pass in a lambda function to tell how the sort has to be. It says the k closest. Read it again. K closest to the origin. Right. So it's k closest to the origin, which I don't know. I don't think this is too special. So what we can do is just sorted points, right, and then key equal to lambda. We'll go to point, and then we don't have to do sqrt because we can just do basically just because we to the origin, right? So it's just p0, right, plus p1. We sort based on this, and once we're done, we take the first k. Yeah. Like, is there a smarter way to do this? I don't know. Let's take a look. Yeah, pretty sure this is it. Yeah, this is it. What? I don't know. I don't know what this question is going for. 648, 83%. Maybe, I don't know, Maybe we cannot use sorting? I don't know. $9.73, right? I don't know where this problem is going. Maybe it is trying to test a specific concept, but for me, it's as straightforward as sorting. So I'll be O n log n because it's sorting, and then, well, try to think. What do you think can be the point of this problem? I honestly don't know. I mean, no idea. Honestly, no idea whatsoever. What are you trying to test? I see the solution. Of course. Yeah. Sort of custom comparator, that's exactly what it is. Yeah, this is a, if that's the only thing, then max heap. I think you push it to the max heap and then you pop. It's the same thing. O n log n. Okay, O n log k. Right? O n log k. It's not O n log n. Because you don't only do it k times. Okay. Wait, hold on. Hold on. So the first k elements in the heap. Oh, this is what you're trying to test. So we keep the heap of 2 elements, right? So sometimes if something that is smaller, then we will push in. If something that's smaller than whatever's in it, we'll push in. So the top will always be the smallest, because every time we push in is something that's smaller than. Wait, hold on. Should we hold a max heap, right? Yeah, it's a max heap. It's not a min heap. It's a max heap, which means whatever is in it is going to be the maximum. Wait, hold on. A max heap to find the k minimum values. So inside we have the maximum value, and everything is smaller than that. Okay, so if I find something smaller, I'll push into this max heap, and the max heap will push the current max to the top, and then we can be sure that, oh yeah, so we keep it at 2. Like if I want to find the top 2, we just have a max heap of size 2, and then whenever it is smaller, something that is smaller than the top, we push it in. Now we can, if something is smaller than the top, we pop the top and then push the smaller one in. Ah, that is actually smart. Yeah, push pop, exactly. Huh, nice. Yeah, that's actually quite nice. Okay, this is actually, okay, I see where this one going at. Heap is a good idea. So it has a more general connotation, right? So the more general connotation is for if you want to find the k smallest values, the k largest values. Of course, you can sort it, which will be O(n) log n. Well, actually, technically, O(n) log n, yeah, and k, right? So technically it's like that, but it'll be faster is O1 log K. I'm actually going to write this. What about binary search? Want to give us ON? Holy guacamole! It is ON. Quick select. Oh my goodness. Oh, this is deep. Ah. Alright, I can do max heap. You know what? One step at a time. Let's do the heap. Let's do the heap solution. A heap solution is definitely a good one, which I should be able to think about this. Hold on. Alright, I'm back and let's do the heap solution. So this is where this problem is going at. Heap solution. Very good. And this shall be the standard for us going forward. Anytime if the requirement is to find the k smallest or k largest values in the list, we shall use heap. Alright, so this is going to be O(n) log k, right? It should be faster. So how are we going to go for it? Well, of course, we're going to have a heap. It's going to be this, right? And then I'm going to say for point. We can actually say for x, y in points. Right, for x, y in points. And then we save. Yep. I see why they do this. Enumerate points, right? So we do this, and then we say if len heap is smaller than k, then heap.heap push heap, and what do we push? We push index, right? But before index, we need a distance, which is x plus y. But we want to keep a max heap, even though we get the minimum k values, but we keep a max heap. So if it's a max heap, we need to do this. All right, so we do this. Else, which means it's equal to k. So when it's equal to k, then we say if, actually every time we need to have a dist. We actually do this. Distance equals this, right? And then it can just minus distance. And I would say if, it's only, I'm going to do elif. Elif, right, dist is actually minus dist. So the distance is smaller than heap 0, 0, negative, right? Which means if it's a smaller, right? So the distance is smaller than the top. Then we're gonna call heap q.heap push pop, right? Heap. So we pop the one that's bigger, and I push the new one, right? So we do this, we go through the entire thing, and at the end, we're going to return points I, right, for I, for this I in heap. Okay, let's try this. Oh, shoot, heap Q. Oh. Yep, this one seems to be correct. There we go. That's good. Okay. Solution 3. All right, keep reading. Now, this is a good problem. So we have binary search. How does binary search work in this case? First K sort of points. A defined target condition and a set of range. Modify the standard method. Choose a target distance, and then we would iterate through every point during each binary search loop to check if our target distance contains exactly k points. If it contains less than k points, we'll increase our target distance until we find a target distance that contains exactly k points. So we have this, and then we try to see if it's k, and if it's not, we'll increase. Yeah, that is O n log n. Improve upon the time complexity by eliminating one set of points at each end of each iteration. If the target distance yields fewer than k closer points, then we know that each of these points belongs in our answer and it can then be ignored in later iteration. If the target distance yields more than k, we know that we can discard the point that fell out of the target distance. Having the remaining points in each iteration of as true. Each iteration. And this is repeat. Okay. Closer array contains fewer than k points. We can add those points to our answer, yes, and adjust k to reflect the number of points still left to be found. Two arrays. So if we given a k, a distance, and then we started filling those two arrays, right? So we go through O n, and after we go through, if we are in the, if our distance is in the middle, right? If our distance is in the middle, then we'll have a half and a half, and we see the left half is smaller and the right half is bigger, so the bigger half we don't have to worry about. We go to the smaller half if the smaller half is more than k. and then we pick the middle point again. Okay. I see the implementation. So we get a distance. Yes. Self-Euclidean distance. Yeah, so we got the distance. Low, high, and I have the closest. Closest to the father. And if length closer is larger than, remaining equals closer. High equals mid. Otherwise, K, this is the one we define. So closest dot extend closer. Wait, this is the closer, so closest is not. Why closest dot extend? Closer, remaining equals farther. Oh, closest, that's the result. That's the result. And we keep going. I see. Yeah, so the first is n plus n over 2, n over 4, all the way down. And then this one will give us on in general. Yeah, I mean, all we need to do is to find the initial low and high, right? Find the low and high, so it's guaranteed. Oh, it's actually not guaranteed. No, it is guaranteed because I'm searching one by one when it's split. Yeah, I'm searching one by one. So it is guaranteed to be on. Alright, quick select. This does feels like a quick sort, right? So you pick a pivot and put some value on the left, some value on the right. Space complexity to on, yes. Oh, quick select, I see. We're just swapping. Oh my goodness. In place approach. Okay, should always consider whether the quick select algorithm can be applied. That is true. So it's not just heap, it's on log k. This is on. Quick sort, yes. Tony Hora. All right, we go back to quick sort. A pivot value is chosen, yes. The sort function uses 2 pointers, so just start from the opposite end of the range and move inward and swap values in the range. These values are swapped as necessary, yes, to ensure that the values lower than the pivot are on one side and the remaining higher is on the other side. Once the values are thus partitioned, the quick sort function can be recursively calling each partition and sorted, and it can sort by on log n. Exactly, that's quick sort. If we don't care about the fully sorted, which means we don't have to go both sides, right? We just pick one side and that's O. Isn't that log n? We don't care about fully sorting array values. Instead, we only want to make sure that we select the first k, but we can simplify this process. At each recursive branching of the quicksort function, we can ignore the partition that does not include the kth value. This is the basis, yes. This is the same as binary search, but in place. Two resulting partition in each state that we no longer need to use recursion to branch. So yeah, everything goes down to one path. 2 pointers, yes, that define the entire range. How do you choose pivot? It should be a random one, all right, for the pivot. Closer the pivot is to the medium, the more likely each successive partition is to suitable. Yes. A common method of selecting pivot including picking the first, the last, and middle index. You need some random process. The range nearly sorted, for example, picking the first or last can lead to worst case. That's true. Middle index. Okay, we choose middle index. Okay. I think I'll just use the start. That'd be easier. No, I think I choose the middle, swap it to the start, and then go for it. Yeah, I think I can do this. I can do the rest myself. So I am not going to try to read this. All right, let me think about this quick select. So basically we have, it's the same problem as just we have, I mean the distance is just a distraction, right? It's just a distraction. It's fine. But I mean in my case, I do think we shall create another list. Because if not, we have to compute every single time the distance. So, okay, let's just try like pure space, like O1 extra space. Okay, O1 extra space. So I have a bunch of things. So we pick the middle point, and then we can swap with the first one. Okay, and then we have 2 pointers, left and right. And then what do? We compare left, right? If left is smaller, then so we'll put the smaller on the left and bigger on the right, right? So the left, if it's smaller than the start, then left move forward. And if left is larger than the start, then we swap, right? And after swapping, we left do not move, but the right move to the left. Okay, and then so we'll keep going until the left is smaller than left to move forward, right? And eventually, this process keeps going, and the left and right will meet in a certain place. Now, because the right doesn't move by itself, we only move on the left. So the left will swap, and the right move forward, and if it's smaller, then left move forward, then we meet. Okay, so it's the left move forward, then we meet, or left we will swap, and then right move forward. Right moves to the left, and then we meet. So whatever happens, the left, when they meet, it shall point at a position. I think it's bigger. It could be smaller. It could be. It could be bigger or smaller than. Yeah, I mean, it could be. I mean, think again. So it's smaller, then we move forward, right? And then we move forward, we don't know when they meet each other. It could be smaller or it could be bigger. So I think my idea is when we get out, we have to compare that one to the pivot. If it is larger than pivot, then we're gonna swap with this one. If it is smaller than pivot, then we're gonna swap with this one. Okay, think one more time. So if it is smaller, right, then I move forward, and that's when we can get out. But we get out, We don't know if this is pointing to a bigger or smaller, huh? If it's bigger, and I will swap with whatever it has. So it's bigger, so this point forward, and that could be a smaller one, right? So yeah, we can try. Let's try this. So the technically ON solution using quick select. Yeah, according to the official solution, quick select should be the first algorithm that comes to mind when we want to find the first k smallest or biggest value without them being sorted. Okay, so in this case, I think I'm just gonna pick the first one as pivot. It's like, who knows? Technically, it doesn't matter. So we're gonna pick the first one, the last one. Oh, we haven't solved it yet, right? We just solved this, so we put the pivot into the right position. Now we need to see how many, right? And if it's equal to k, then we just return whatever the front is. If it's bigger than k, then we pick a pivot in the middle of these. Maybe the middle is a better way. We pick a pivot in the middle of these, and then on the left side we keep going. If it's not, then we're going to start from this to the end, and then we pick a new value. Okay, so what is the overall loop? Well, the overall loop is while true. I like to go while true. I like to go while true. Okay, so k, right, and the pivot. So mid will equal to. Do need left and right. So left, right is equal to 0 and len points minus 1, right? So mid is equal to left plus right divided by 2. I'm using the midpoint, and when you use the midpoint, I'm going to swap with the front. And then we just say points mid, points left, points mid equals to points mid and points left. Okay, we do the swap. Now we're going to have the left and right, and the low and high. So low shall equal to left plus 1, high shall equal to right. Right, that's low and high. We have low and we have high. Now it's going to be while low is smaller than high. Okay. Then I'm going to see if points low 0. I see why they use function. Yeah. So dist point. I'm gonna call it point is gonna be a list of integers. All right, and this one will return an integer. And I return point 0 square plus. Actually, it's distance square. Too much trouble. 0.1 square. Okay, that's the function. Then we just can say if self dot dist points low, right? So if this distance, I'm going to actually pre-compute the pivot distance. So the pivot distance is equal to self.dist points left, right? That is, actually, it's easier to do it here. The mid, right? And then we swap it and we get this. Okay, so if this is smaller than pivot distance, right? If it's smaller than pivot distance, then low plus equal 1, right? Else, then we do points low, points high equals points high, points low, right? So we swap low and high, and after swap, high minus equal 1, and then we go to the same. Now this blah 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 blah. Once it's done, something will pop out, right? Low will pop out, and then what we're going to say is if self.dist points low, if this one is larger than pivot distance, then low minus equal 1, right? Because if it is smaller, it's guaranteed that we'll move forward. Hold on, could it be that the high, it's guaranteed that the high plus 1 will definitely be larger, right? High plus 1 will definitely be larger, and then they meet with high. What we don't know is if high itself is larger. High itself, it might be larger, that's why I need this. So now we have this, then we do one more swap. Then we do points left, points low, because low is smaller, equals to points low, points left. So this is put pivot in place. So now pivot is in the place, and it's equal to low. Now we're going to say is if, all right, if low, so low is the pivot, right, the pivot, and then to the left is all smaller than pivot. So if low is equal to k, right, if low is equal to k, then we simply return points k. That's it, we're done. Else, if low is larger than k, right? If low is larger than k, then we need to shrink. We need to say right is equal to low, right? So we need to shrink it down. So what we're saying is low is larger than k, so there are k value that's larger than the pivot. So that's the small. So we have too many. Sorry, we need to shrink it down. So the right shall be this position, right? Right shall be this position, okay? Now we need to try to find it within this, right? Try to find it. Else, low is smaller than k, right? Low is smaller than, so we have pivot and total number to the left of pivot is smaller than k. So we need to go from pivot, so left need to equal to k, right? So the left need to equal to k. K. Wait, k, not k, low. So left equal to low, right? And then k shall minus equal to low. Because we have that many values, we can already eliminate. So that's that. And we do need a rest. But when do we get out? Yeah, I don't think we need a rest. Which we shouldn't. Let me think again. Every time we hit on a low, right? And then it shouldn't be low though. It should be low minus left, right? That's the number of things on the left side. Low minus left, and right equals low. Yeah, and then we do the same thing. We come up and we do blah blah blah, the same thing. Pick a pivot and then we do this, and then find a new. So if it's smaller than k, then we say left equals low, right? And right is this, and then k will minus equal to k minus equal to low minus left. So we take these away. What's the end game? Too small, right equal to low. Shouldn't this be left smaller than right? And when this one just break, right, which means we're done. So eventually, when this whole thing break out, low minus left is equal to k. So when this one left is equal to right, shouldn't we just return left? It's low, right? It's low. So I think what you need to do is return points low. Oh, I'm not sure about this. Let's try it. Okay, so far so good. Let's see. Nope. I think we had a problem. So the left never equal to right. Oh, the distance is the same. Good point. Good point. The distance can be the same. Never mind. We will correct it. It's fine. We have a bunch of test cases. I haven't run a test case. Okay, what's the result for this? So the first one, that's the second one. Okay, and problems that we have is with this. And the answer shall be this. Okay, so we have points, k, right, and this is k closest, points k. If sorted, yep. All right, so the problem is, I need to handle this one. What if it's equal to pivot? Too small, hold on, the two smallest, it shouldn't matter. Come on, output 1. Let me think. So the midpoint is going to be this one, right? And then 0 plus 1, the other 2 is 0. And then I got pivot, distance, and swap. So low and high will be pointing both at this. And then boom, it'll come out. Okay? And then come out. If this is larger, then it's actually not, it's equal to. So low doesn't change. Low is right here. Okay, so low is right here, so it's not larger than. And then I swap these two. Okay, so this one comes here. Yes. And low minus left, because it's 1, is not equal to. Low minus 1 is 1, is smaller than k. So I say left equals low. So left comes here. So left is here. Right? And k minus k is 2. 2 minus 1 is 1. So left is here. And 1. So left and right point into the exact same position. So left and right points in here. They point to the same one. And we have k equals 1. And again, we don't go through this. But we immediately gets out. How do we reconcile this? So imagine low is a pivot, right? So we're saying we need to include the pivot because in this scheme, pivot is never included. It's never included. What if I include the pivot? Because if I don't include the pivot, right? If I don't include the pivot and low minus this is smaller, and I include the pivot in the next round. But in the next round, in this case, next round never run unless I say left is smaller or equal to right. Okay, if left is smaller or equal to right, if left is smaller or equal to right, so I'll have one more chance, right? Come in, after mid, I'll have this, and low equals left plus 1. This one doesn't run, right? Then, this one will come out, so low is too big. What's the right way to do this? What if we include? So below minus left plus 1. Then we will do low plus 1. And if this one is larger than, what if we do this? Right, we say well, it's going to be plus 1. Right, and then we're going to do plus 1. And I say this plus 1 is larger than k. So including the pivot is too much. Right? If we're including the pivot, it's too much. Then right equals a low. Otherwise, if including the pivot is not enough, if including pivot, that's not enough, and then left, we can actually do left equals low plus 1, k, or equal minus equal to low minus left plus 1. Something like this. Then this one pass. And this does not pass. What? The hell? I have 3, 3, and this and 5. It would be 3. Are we including all 3? Alright, I need to see what's the standard practice. Choose pivot. Quick select. Pivot index. Oh, hold on. Maybe the problem is not with this. Maybe the problem is not with this. The problem is it should be k. Right? Because we want a k smallest, and it's guaranteed after all this process we'll have the k smallest already done. Like low and high, it doesn't really matter. Alright, I'm gonna go through this one more time. So we got a left and right, which is the range, the total range. And then we pick the midpoint, and then we use the pivot, okay? And then we go through this process to swap things, such that after this, so this will guarantee that points low is the pivot position. Actually, after this, the pivot position is at the right position. So the pivot is at the right position. And then we count. The low minus left is the total number of points to the left of the pivot. And that is equal to k, and we're done. We have found k smallest values. If it's not, if it's too big, and then we put the right to the low. We put right to low, so we shrink down the total number of range, and then we do it again. Otherwise, we put left to low, right? And we increase the range, and then decrease the total number we want to find. And at the end, we return, okay. So basically we're saying this is all fine. Just instead of return, I'm going to return k. Right? Let's try this. See if this one works. Nope. There's two problems with this. How? Alright, let's see. Have
sure you eat this first. So you after you cook, you put these to the top or whatever. So you will eat these first.
Okay, so let's see why we have time limit. So basically, low and left does not converge. I think that's why. Which makes sense because the lower left, they do not move forward. Let me see. So the point we have is 10, 8, 8. So 10, 8, 8. So I'll say the first point is going to be 8, 8, and then we start finding the first one. If this is smaller than pivot, no, it's larger than pivot. So I swap. 8 is here, 10 is here, and high comes here. All right, come out. Oh, so we get out. Now, so if this is larger than pivot, since no, it's not larger than, therefore, then we swap it. Okay, now this is our low. Okay, the K is 2. So we say low minus left, so 1 minus left is 1, is smaller than K, right? So we go left is here. Okay, and right is here. Then we say K minus equal to 1, so K equal 1, so this we need to find 1. Okay, that's fine. So left right is here, left is smaller than right, that's true. Mid is going to be left. Pivot is this doesn't change. Low equals left plus 1, so low is here, and then immediately jump out. And then if self distance is larger than pivot, yes, so low comes here, so low points into here. And low minus left is 0. 0 definitely smaller. Then left equals low. That is the point. That is the problem. That is the problem. That is the problem. So we're pointing to the same position all the time. How do we solve this? Well, we solve it by, so one of these need to make change, right? So if low minus this is a smaller than K, and larger than K, we can do either this one minus 1, or we can do this one plus 1. Then which one makes more sense to me? So low minus left is the total number that's smaller than the pivot. The total number that's smaller than the pivot, right, then we shall tighten it even more. And if the total is larger than, right, total is larger than, if it's larger than the left, now we need to include low. So I think what I do is we add here. Okay, so this is what I think. And the answer shall be minus 2, 2. Right? And then 2 minus 2. That's what I think. And of course, we're going to say this one minus 1. Nope. Shoot. Wait, that's still not right. Oh yeah, because we never hit this position. Huh. Let me think again. It's smaller than K, right? It's smaller than K. Then how about this plus 1 as well? Because we know low is the pivot, and the pivot is in place, right? So if the left of the pivot is, in this case, it kind of makes you think, right? It kind of makes you think. I shall include the pivot as well, because pivot is sorted. Okay, let's just include the pivot. is now if this plus 1 is larger than k, right? Which means including the pivot, we have too much, right? We have too much. So right will be discard the pivot, okay? Otherwise, if including the pivot is too small, right, then left going to be plus 1, right? And then this one going to be plus 1 as well. There we go. Okay, so include the pivot to make it tighter, to make the whole thing tighter. So let me say include pivot in consideration. Try this. Oh my god. Nope. It ain't right. Why though? Would include a pivot is not right. Include a pivot is larger than k. Yeah, this is frustrating. Yeah, seems like I don't have time to do the other problem. Expected. Okay. Why is that? If I include a pivot, right? Otherwise, if include a pivot is too much, then right shall equal to low. I don't know, just playing around. Yeah, still not right. Not include a pivot. If I do not include a pivot, then the left side is too big. I say right minus 1, right? Otherwise, if left is too small, then something's not right. Swap, I don't think this should be right. Which one I got swapped? Yeah, I might as well just sort it. The problem is I did not including this. There is this. Bob. Oh, this one's smaller. How come this one's not included? Okay, I'm gonna do this. So I'm gonna print points, right? And pivot. Okay. So pivot is at position 2. 0, 1, 2. Everything to the left is all good. And we're looking for. What we're looking for is 10. So we're looking for 10. Okay. So this is the pivot. And to the left, we have these two. That's smaller than this. Everything to the right is bigger than this. Okay. Then I say low minus left is not equal to k. Low minus left. I know what, L plus 1. Because this is in position, so all of these is the smallest, right? 3, 1, 3. If equal to k, then break. Otherwise, if this is larger than k, which means it's too much, I know this is sorted. So I can write equals to low minus 1. Because this is larger than k. So if I do this minus 1, this could be equal to k. Right? This could be equal to k. Otherwise, if this is smaller than k, so including this is smaller than k, then we say left need to equal to low plus 1. Right? And then we do this. And we run it, and we still fail. Okay, we still fail, but now we can try to figure out why we fail. So that's 3. It's more than k, so left. I can actually also do at the beginning. We can do before. Print left to right. Okay. So after this, left is 3, right is 16. 0, 1, 2, 3. So this is the left. Right? This is the left. And then low is equal to this. And then blah, blah, blah. And then we're done. Points. And the low is now 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is 11, right? 11. And if it's 11, low minus left, left is 3. 11 minus 3 is 8, right? Plus 1 is 9. What is k? K is 10 minus, you know what? I also can just get a k as well. Okay. K does not change. That how is that possible? How is k not changing? Low is 2. Yeah. How is K not changing? What? Low is 2. Left is 3. Oh, shoot. Should do this before we change. Oh my god. Alright, we're still wrong, but. Okay. Oh, shoot. Shoot. Ah, I know. Oh my god. My god. That should be K, right? And now I don't need this. This. Okay, the remaining. And remaining. And now it got me thinking. What if we don't include the pivot? What if we don't include the pivot? If we don't include the pivot of the left part, right? Now we say if the left part is larger than, then right equal to this. That makes sense. If the red part is smaller than, then I say remaining with this red part, then left will equal to this. Ah, this one doesn't work. We have to, left has to plus. Right? Left has to plus. But we say this is larger than. Which is fine. We can actually do it because we say, so low minus of this part, I say this part is smaller than, right? This part is smaller than. So I can including low, which is fine. I can always including low because rem is, this one is smaller than rem. So this plus 1, right? So this plus 1, I include, right? I include the pivot. I include the pivot, and it works. So including the pivot. You know what? Yeah, I think it's easier just including the pivot. So include pivot in consideration. Yep. Okay, let's try this. So this is including the pivot. It works. So we do have to include the pivot. All right, that will be it. It's a good question. I'll see you guys tomorrow. Adios.